Here's a question that will break your brain if you think about it for too long. What existed before the Big Bang? Now, before you confidently blurt out nothing, let me stop you right there, because that answer opens up an even more disturbing question. How can nothing exist? Think about it. Close your eyes and try to imagine absolute nothingness. No space, no time, no darkness, because darkness is something. No quantum fields, no energy, no potential for anything. Just pure, absolute void. You can't do it, can you? Your brain literally cannot conceptualize true nothingness because the very act of conceptualizing requires a mind, which is something, existing in time, which is also something. We are creatures trapped in existence, trying to understand non-existence using tools that only work within existence. It's like a fish trying to understand what it means to be dry. And yet, here we are, armed with mathematics and physics and an unhealthy obsession with questions that make our heads hurt, attempting to answer the single most profound question in all of science. What came before everything? The weird part is, we might actually have some answers. Or at least, we have some really fascinating, educated guesses that are based on actual physics rather than wild speculation. But fair warning, none of these answers are going to feel satisfying in the way you probably want them to be. In fact, some of the leading theories suggest that the question itself is fundamentally broken. That asking what came before the Big Bang is like asking what's north of the North Pole. The question contains a grammatical error written in the language of physics. But we're getting ahead of ourselves. Let's start with what we actually know, because the story of how we figured out the universe even had a beginning is almost as wild as the theories about what came before it. For most of human history, the prevailing assumption was that the universe was eternal. It had always existed and would always exist. This made intuitive sense because, well, if the universe had a beginning, that immediately raises the uncomfortable question of what caused that beginning. And we're right back to the brain-breaking paradox. Even Albert Einstein, whose general theory of relativity would eventually provide the mathematical framework for the Big Bang theory, initially believed in a static, eternal universe. In fact, he was so committed to this idea that when his own equations suggested the universe should be either expanding or contracting, he added a fudge factor called the cosmological constant to keep everything nice and static. He would later call this the biggest blunder of his career. The first crack in the eternal universe model came in the 1920s when astronomer Edwin Hubble, using the newly constructed Hooker telescope at Mount Wilson Observatory, made an observation that would change everything. Hubble was looking at distant galaxies, and he noticed something weird. The light from these galaxies was shifted toward the red end of the spectrum. Now, this red shift, as it's called, is caused by the Doppler effect, the same phenomenon that makes an ambulance siren sound different as it approaches and then moves away from you. When a light source is moving away from you, its wavelengths get stretched out, shifting toward the red end of the spectrum. And the faster it's moving away, the more dramatic the shift. What Hubble discovered was that not only were distant galaxies moving away from us, but the farther away a galaxy was, the faster it was receding. This wasn't just galaxies drifting apart through space. This was space itself expanding, carrying the galaxies along with it. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, every dot moves away from every other dot. Not because the dots are moving across the surface, but because the surface itself is expanding. That's what's happening with our universe. The space between galaxies is stretching. Now, if space is expanding, that means if you run the clock backward, everything must have been closer together in the past. Keep running it backward far enough, and you reach a point where all the matter and energy in the universe was compressed into an infinitesimally small, infinitely dense point. Georges Lemaitre, a Belgian Catholic priest and physicist, was one of the first to extrapolate this conclusion from Einstein's equations. In 1927, he proposed what he called the hypothesis of the primeval atom, suggesting the universe began from a single point that exploded outward. The term Big Bang came later, coined somewhat mockingly by astronomer Fred Hoyle during a BBC radio broadcast in 1949. Hoyle was a proponent of the steady-state theory, which held that the universe had no beginning and continuously created matter to maintain constant density as it expanded. He thought Lemaitre's idea was absurd, and he used the term Big Bang to ridicule it. The name stuck, though it's actually a pretty terrible name for what happened. For starters, it wasn't big. At the moment of the Big Bang, the universe wasn't expanding into a vast empty space. The universe was the size it was, whether that was infinitesimally small or already infinite, depending on which model you prefer. And it wasn't a bang. There was no explosion of matter flying outward into pre-existing space. Instead, space itself came into existence, or began expanding, and matter and energy came along for the ride. A better name might be the everywhere stretch, but that doesn't have quite the same ring to it. For decades, the Big Bang theory remained controversial. The steady-state proponents argued that if you couldn't observe the moment of creation, you couldn't prove it happened. But then, in 1964, two radio astronomers named Arno Penzias and Robert Wilson were testing a new antenna at Bell Labs in New Jersey when they detected a persistent background noise that wouldn't go away no matter where they pointed their antenna. At first, they thought it might be interference from New York City, or maybe pigeon droppings on the antenna. Yes, really. They even trapped and removed the pigeons and cleaned out the droppings, but the noise persisted. What they had accidentally discovered was the cosmic microwave background radiation, or CMB, a faint glow of light that fills the entire universe. This radiation is essentially the afterglow of the Big Bang itself, the cooled-down remnant of the incredibly hot, dense state the universe was in shortly after it began. When the universe was very young, it was so hot and dense that matter existed as a plasma of charged particles. Light couldn't travel freely through this plasma because it kept scattering off the charged particles, like trying to see through fog. But about 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, photons could travel freely through space. The light from this moment has been traveling through space ever since, and as the universe expanded, its wavelength stretched from visible light into microwaves. That's what Penzias and Wilson detected. The discovery of the CMB was the smoking gun that convinced most scientists the Big Bang had actually happened. Penzias and Wilson won the Nobel Prize for their accidental discovery, though they had to share the credit with the pigeons in spirit. Since then, we've measured the CMB in exquisite detail using satellites like SOBE, WMAP, and Planck. These measurements have allowed us to determine the age of the universe with remarkable precision, currently pegged at 13.8 billion years, give or take a few tens of millions of years. We can see tiny temperature fluctuations in the CMB, variations of only a few millionths of a degree, that represent the seeds of all the structure we see in the universe today. Regions that were slightly denser attracted more matter through gravity and eventually formed the first stars, galaxies, and galaxy clusters. But the CMB isn't the only evidence for the Big Bang. There's also the abundance of light elements. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur, but it was expanding and cooling so rapidly that fusion only lasted for a brief window of time. During this period, called Big Bang nucleosynthesis, protons and neutrons combined to form the nuclei of light elements, primarily hydrogen and helium, with trace amounts of deuterium, lithium, and beryllium. The Big Bang theory makes very specific predictions about the ratios of these elements, and when we observe the universe, particularly in regions where stars haven't had time to alter the primordial composition, we find exactly the ratios the theory predicts. About 75% hydrogen, 25% helium by mass, with tiny amounts of the other light elements. This is not a coincidence. It's a prediction that came before the observations confirmed it. So we can say with a high degree of confidence that the Big Bang happened. About 13.8 billion years ago, the universe was in an extremely hot, dense state, and it has been expanding and cooling ever since. Everything we can observe, all the matter and energy, all the space itself, can be traced back to this moment. But here's where things get philosophically uncomfortable. If the Big Bang was the beginning of space and time, then what does it even mean to ask what came before it? The word before is a temporal concept. It requires time to exist. If time itself began at the Big Bang, then there was no before. It's not that there was nothing before the Big Bang, it's that the concept of before doesn't apply. Let me try an analogy that might help or might make things worse. Imagine you're standing at the North Pole. If I ask you to walk north from there, you can't do it. It's not that there's a wall blocking you or that something terrible will happen if you try. It's that the direction north loses its meaning at that location. Every direction from the North Pole is south. Similarly, if the Big Bang represents the beginning of time, then asking what came before is asking for a direction in time that doesn't exist. Stephen Hawking used this exact analogy in his book, A Brief History of Time, and it's a pretty good one as far as analogies go. But, and this is a big but, just because something is hard to conceptualize doesn't mean we should stop trying to understand it. Maybe our intuitions about time are wrong. Maybe time didn't begin at the Big Bang in the way we think it did. Maybe there's a more fundamental reality that transcends our everyday notions of cause and effect, before and after. This is where modern physics gets really interesting and really weird. You see, our best description of the Big Bang comes from Einstein's general theory of relativity, which describes how matter and energy curve spacetime, and how that curvature affects the motion of matter and energy. It's an incredibly successful theory that's been tested and confirmed in countless ways. But when we try to use general relativity to describe the very first moments of the Big Bang, we run into a problem. As we go back in time, the universe gets smaller, denser, and hotter. Eventually, we reach a point where the density and temperature become infinite. This is what physicists call a singularity, and it's a big red flag that our theory is breaking down. Infinities in physics are usually a sign that you're trying to use a theory outside its domain of validity. It's like trying to use Newtonian mechanics to describe objects moving near the speed of light. Newton's equations will give you nonsensical answers because they weren't designed to work in that regime. You need special relativity instead. Similarly, when we try to describe the universe at the incredibly small scales and high energies present at the Big Bang, general relativity starts, giving us nonsensical answers. This is because general relativity is a classical theory, meaning it doesn't account for quantum mechanics, the set of rules that govern the behavior of matter and energy at subatomic scales. At the Big Bang, the entire universe was subatomic in size, so quantum effects should have been enormously important. What we need is a theory of quantum gravity, a way of describing gravity that's consistent with quantum mechanics. And here's the problem. We don't have one. Not a complete one, anyway. This is one of the biggest unsolved problems in all of physics. There are several candidates, string theory and loop quantum gravity being the most prominent, but none of them are complete, and none have been experimentally verified. Without a theory of quantum gravity, we can't actually describe what happened at the very moment of the Big Bang. We can get very close, down to something called the Planck time, which is about 10 to the negative 43 seconds after the Big Bang. That's a decimal point followed by 42 zeros, and then a 1. At this point, quantum effects of gravity become important, and our equations break down. Everything before the Planck time is essentially a black box. We can make educated guesses based on our incomplete theories of quantum gravity, but we can't be certain. And this is where the question of what came before the Big Bang actually becomes a scientifically meaningful question, because different theories of quantum gravity make different predictions about what might have existed before, or whether before even makes sense. Some theories suggest the Big Bang wasn't actually the beginning, but rather a transition from a previous state. Others suggest that time itself might be an emergent property that arose from something more fundamental, and that asking what came before time is indeed a meaningless question, but for more subtle reasons than the North Pole analogy suggests. Before we dive into these theories, we need to address something that's going to come up again and again in this discussion, and it's something that causes endless confusion among non-physicists. When physicists talk about nothing, they don't mean the same thing philosophers mean when they talk about nothing. To a philosopher, nothing means absolute nothingness. No space, no time, no matter, no energy, no physical laws, no mathematical structures. Complete and utter void. To a physicist, nothing usually means the quantum vacuum, which is actually a seething foam of activity. Even in the darkest, emptiest regions of space, far from any matter or radiation, quantum fields are still there, and they're never truly at rest. This is because of the Heisenberg uncertainty principle, one of the fundamental principles of quantum mechanics. The uncertainty principle states that certain pairs of properties, like position and momentum, or energy and time, cannot both be known with perfect precision simultaneously. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of our measuring instruments. It's a fundamental feature of reality at quantum scales. One consequence of this principle is that the vacuum is never truly empty. Pairs of particles and antiparticles are constantly popping into existence and then annihilating each other almost immediately. These are called virtual particles, and while they exist for only the briefest instant, they have measurable effects. For example, virtual particles cause what's known as the Casimir effect. If you place two uncharged metal plates very close together in a vacuum, they'll actually experience a tiny attractive force pushing them together. This happens because the space between the plates suppresses certain wavelengths of virtual particles, so there's less quantum activity between the plates than outside them, creating a pressure difference. The Casimir effect has been measured in laboratories and confirmed to exist, which means virtual particles, despite their fleeting existence, are real. The quantum vacuum also has what's called zero-point energy. Even at absolute zero temperature, where all thermal motion has ceased, quantum fields still have a minimum energy they can't go below. This is another consequence of the uncertainty principle. If a quantum field had exactly zero energy, we would know both its value and its rate of change with perfect precision, which the uncertainty principle forbids. So, even empty space has energy inherent to it. Now, when physicists like Lawrence Krauss write books titled A Universe from Nothing, they're talking about a universe arising from this quantum vacuum, not from absolute philosophical nothingness. And this has caused some rather heated debates. Philosopher David Albert famously wrote a scathing review of Krauss's book, arguing that the quantum vacuum is not nothing. It's a quantum mechanical system with a very definite structure, obeying very specific rules. It's something, just a very sparse and odd something. Krauss fired back, arguing that Albert was playing semantic games and that the quantum vacuum is the most nothing-like thing that can possibly exist within the framework of physics. Both of them have a point. Krauss is right that if you're trying to understand how the universe came to be using the tools of physics, the quantum vacuum is the right concept to work with. It's the ground state of reality according to our best theories. But Albert is also right that this doesn't really answer the deeper philosophical question. Why does the quantum vacuum exist? Why are there quantum fields with these particular properties? Why these laws of physics and not others? Or why any laws at all? This is what's sometimes called the Leibnizian question, after philosopher Gottfried Wilhelm Leibniz, who famously asked, "Why is there something rather than nothing?" It's the ultimate question, and it's not clear whether physics can ever answer it, or whether it's even the kind of question that admits a scientific answer. But let's table that philosophical quandary for now and focus on what physics can tell us. Even if we can't explain why the quantum vacuum exists, we can ask whether the quantum vacuum is stable, and if not, what it might transition into. And here's where things get interesting. In quantum mechanics, systems can tunnel through energy barriers that would be insurmountable in classical physics. Imagine a ball sitting in a valley surrounded by hills. Classically, if the ball doesn't have enough energy to roll over the hills, it's stuck in the valley forever. But quantum mechanically, there's a small probability that the ball can tunnel through the hill and appear on the other side, even though it never had enough energy to go over the top. This sounds bizarre, but it's a well-established phenomenon that's been observed countless times in laboratory settings. Quantum tunneling is responsible for radioactive decay, for how some chemical reactions proceed, and for the operation of devices like tunnel diodes and scanning tunneling microscopes. Now, here's the wild part. If quantum tunneling is possible for particles, why not for entire universes? This is the question that physicist Alexander Vilenkin asked in the early 1980s, and his answer was, there's no reason why not. Vilenkin proposed that the universe could have tunneled into existence from literally nothing, or at least from a state of nothingness. In his model, nothing is represented by a particular quantum state with no space, no time, no matter, no energy. But this state is not stable. Quantum mechanics allows for the spontaneous creation of a tiny bubble of space-time, a seed universe, through quantum tunneling. This bubble would be incredibly small, on the order of the Planck length, which is about 10 to the negative 35 meters. That's a billion times smaller than a proton. Once created, this seed universe could then undergo a period of rapid expansion called inflation, which we'll talk more about later, and grow into something resembling our universe. The probability of this happening is extraordinarily small, but in quantum mechanics, anything that's not explicitly forbidden will eventually happen if you wait long enough. And if you're starting from a truly timeless state. Long enough is not a problem because there's no time to wait through. Time only begins once the universe tunnels into existence. This is deeply counterintuitive because we're used to thinking of cause and effect as a temporal sequence. The cause happens first, then the effect follows. But in Vilenkin's model, there is no before in which a cause could operate. The universe doesn't need a cause in the traditional sense because causation is a concept that only makes sense within time, and time begins with the universe. The universe simply is. It exists as a quantum possibility that actualizes itself. Now, I know what you're thinking. This sounds like mystical nonsense, like we've given up on science and started making things up. But the mathematics of this proposal is actually quite rigorous. It's based on an approach called the Wheeler-DeWitt equation, which is an attempt to apply quantum mechanics to the entire universe at once. The Wheeler-DeWitt equation is notoriously difficult to work with, and its interpretation is controversial, but it's a legitimate piece of physics, not philosophy dressed up in equations. That said, Vilenkin's proposal has its critics. Some physicists argue that you can't get something from nothing even in quantum mechanics because the quantum mechanical rules themselves are something. You need the laws of quantum mechanics to be in place for tunneling to occur, which means you haven't explained where those laws came from. Others point out that the Wheeler-DeWitt equation has multiple possible solutions, and it's not clear which one, if any, corresponds to our universe. And then there's the awkward fact that we still don't have a complete theory of quantum gravity, so any calculations we do in this regime are provisional at best. But let's dig deeper into this concept of nothing, because if we're going to talk about what came before the Big Bang, we need to be absolutely clear about what we mean when we use that word. And, as it turns out, there are many different flavors of nothing, each one stranger than the last. The most basic kind of nothing that most people imagine is just empty space. You clear out all the matter, all the radiation, every atom and every photon, and you're left with a perfect vacuum. But, as we've already discussed, this isn't really nothing at all. Even in the deepest voids of intergalactic space, quantum fields are still present. Virtual particles are still popping in and out of existence, and space itself still has structure and properties. Space can bend and warp according to Einstein's equations. It can expand, carrying galaxies along with it. It has geometry and topology. It's very much something. So let's go one level deeper. What if we remove space itself? What if we imagine a state with no spatial dimensions at all? No up or down, no left or right, no distance between anything because there's no anything to be between. This is closer to what physicists mean when they talk about the quantum vacuum in certain contexts. It's not empty space, it's the absence of space, or perhaps more accurately, it's the state from which space can emerge. But even here, we're not at absolute nothingness, because if we're talking about quantum states and quantum fields, we're still assuming the existence of quantum mechanics. We're assuming there's a mathematical structure, a set of rules that governs how these fields behave. We're assuming the existence of Hilbert spaces, operators, wave functions, and all the mathematical machinery of quantum theory. And mathematics, as abstract as it is still something. This leads us to one of the deepest and most troubling questions in all of philosophy and physics. Does mathematics exist independently of physical reality? Is it discovered or invented? This might sound like idle philosophical musing, but it has profound implications for our understanding of nothing and whether a universe can come from it. There's a philosophical position called mathematical Platonism, named after the ancient Greek philosopher Plato, which holds that mathematical objects and truths exist in some abstract realm independent of the physical universe. In this view, the number 2 isn't just a symbol we invented or a concept in our minds. It's a real thing that would exist even if there were no physical universe and no minds to think about it. The theorem that the square root of 2 is irrational isn't just something we discovered. It's an eternal truth that was true before humans existed and will be true after we're gone. If you accept mathematical Platonism, then even in a state of absolute nothingness, with no physical universe, no space, no time, no matter, no energy, mathematical truths would still exist. And if mathematical truths exist, then the laws of physics, which are fundamentally mathematical in nature, might exist as well. You could argue that any logically consistent set of physical laws must exist in some abstract sense, and that our universe is simply one particular instantiation of one particular set of laws. But if you reject mathematical Platonism and believe that mathematics is something humans invented as a tool for describing patterns we observe in nature, then you face a different problem. If there's no physical universe, there are no minds to invent mathematics, so mathematics doesn't exist either. But then, how do you describe the process by which a universe comes into being? You need some kind of framework, some kind of rules, and those rules seem inherently mathematical. You end up in a strange circular situation where the universe needs to exist for mathematics to exist, but mathematics needs to exist to describe how the universe comes to exist. This is giving philosophers headaches and has been for thousands of years. Some physicists, like Max Tegmark of MIT, have taken a radical position called the mathematical universe hypothesis. Tegmark argues that the universe isn't just described by mathematics, it is mathematics. Physical reality and mathematical reality are one and the same. In this view, there is no distinction between the physical universe and the abstract mathematical structure that describes it. Our universe is literally a mathematical object that happens to have the property of self-awareness in certain regions, namely, us. If Tegmark is right, then the question of why there's something rather than nothing becomes a question about why this particular mathematical structure exists rather than some other one, or why any mathematical structures exist at all. And his answer is that all logically consistent mathematical structures exist in exactly the same sense that our universe exists. We just happen to find ourselves in this particular one because it's one of the mathematical structures capable of supporting observers. This is a form of the anthropic principle, which we'll come back to later. But many physicists find Tegmark's hypothesis too radical, too much of a departure from the traditional scientific method. It's hard to see how you could test it experimentally, and a theory that can't be tested starts to look more like metaphysics than physics. Let's return to more conventional ground and think about what physicists can actually calculate and measure. One of the most important insights from quantum field theory is that what we think of as empty space, the vacuum, is not unique. There can be multiple different vacuum states, each with different properties and different amounts of energy. This is analogous to water, which can exist in different phases like ice, liquid, or vapor. Each phase is stable under certain conditions, but with enough energy input, water can transition from one phase to another. Similarly, the vacuum of space can potentially exist in different phases. Our universe might currently be in what's called a false vacuum, a state that appears stable but is actually only metastable. It's like a ball sitting in a shallow valley on a hillside. It looks stable, but there's a deeper valley further down the hill. If the ball can somehow get over the lip of the shallow valley, it will roll down to the deeper valley and settle into a more stable state. In the context of the early universe, if the vacuum was in a higher energy state and then transitioned to a lower energy state, the energy difference would have to go somewhere. That energy could drive a rapid expansion of space, which brings us to one of the most important ideas in modern cosmology, inflation. Inflation theory was proposed by Alan Guth in 1980 to solve several problems with the standard Big Bang model. One problem was the horizon problem. Different regions of the universe that are too far apart to have ever been in contact with each other, even accounting for the age of the universe and the speed of light, nevertheless have almost exactly the same temperature. How did they coordinate to be at the same temperature if they've never exchanged information? Another problem was the flatness problem. The overall curvature of space appears to be extraordinarily close to zero, meaning the universe is geometrically flat. But the equations of general relativity say that any deviation from perfect flatness should grow exponentially over time. The fact that we're still close to flat after 13.8 billion years means the universe must have been fine-tuned to an absurd degree of precision in its early moments. Inflation solves both these problems by proposing that the universe underwent a brief period of exponentially rapid expansion in the first fraction of a second after the Big Bang. During this period, which lasted from about 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26, possibly much more. A region smaller than an atom was stretched to the size of a grapefruit or larger. This rapid expansion would have taken a small region that was in thermal equilibrium, where everything had time to come to the same temperature, and stretched it so large that it encompasses the entire observable universe today. That solves the horizon problem. Everything we can see was once close enough together to reach the same temperature. The expansion also solves the flatness problem because it stretches out any curvature. Imagine drawing a circle on a balloon and then inflating the balloon to the size of the Earth. The circle would now look almost perfectly flat because the radius of curvature has become so large compared to the size of the circle. Similarly, inflation stretched the universe so much that any initial curvature became negligible. But here's where it gets really interesting. The energy driving inflation had to come from somewhere, and the leading candidate is a hypothetical quantum field called the inflaton field. Like all quantum fields, the inflaton field would have been subject to quantum fluctuations, tiny random variations in its value from place to place. During inflation, these microscopic quantum fluctuations were stretched to cosmic scales. When inflation ended and the inflaton field decayed into ordinary matter and radiation, these stretched-out quantum fluctuations became variations in the density of matter. Regions that were slightly denser collapsed under their own gravity to form the first stars and galaxies. The pattern of these density variations was imprinted on the cosmic microwave background radiation, and when we observe the CMB with satellites like Planck, we're seeing the stretched-out quantum fluctuations from the inflationary period. This is one of the most profound results in all of science. The structures we see in the universe today, the galaxies, the clusters of galaxies, the vast cosmic web of matter, all of it originated as quantum fluctuations during the inflationary period. Quantum mechanics, which normally operates at subatomic scales, reached out and shaped the entire cosmos. But inflation creates its own mystery. If inflation can happen once, why couldn't it happen again? Or rather, once inflation starts, is there any reason it has to stop everywhere? This leads to the concept of eternal inflation, which might be the most mind-bending idea in all of cosmology. In the eternal inflation scenario, inflation never completely ends. Our Big Bang, the moment when inflation stopped in our region of space and the inflaton energy converted into matter and radiation, was just a local event. Inflation might have ended here, but it's still ongoing elsewhere. And because inflation is driven by a quantum field subject to quantum fluctuations, new regions are constantly dropping out of inflation while other regions continue inflating. Each region that drops out of inflation becomes a universe with its own Big Bang, its own matter and energy, potentially its own physical constants and laws of physics. These pocket universes are causally disconnected from each other because the space between them is still inflating faster than light can travel through it. Yes, space itself can expand faster than light. This doesn't violate relativity, because relativity only says that nothing can move through space faster than light. Space itself can do whatever it wants. So, in the eternal inflation picture, our universe is just one bubble in an eternally inflating mega-universe, often called the multiverse. New bubbles are constantly forming and will continue to form forever into the future. The term eternal inflation is somewhat misleading, though, because while it's eternal into the future, it might not be eternal into the past. If you run the equations backward, you reach a point where inflation must have started. But what started inflation? This is where we're back to the question of what came before the Big Bang. Except now we're asking what came before eternal inflation. One possibility, explored by physicists Arvind Borde, Alan Guth, and Alexander Vilenkin in a famous theorem published in 2003, is that eternal inflation cannot be past eternal. Any universe that is, on average, expanding must have had a beginning. This is sometimes called the BGV theorem, named after its three authors. The BGV theorem doesn't say anything about what that beginning was or what came before it. It simply says that you can't avoid the issue of a beginning by invoking eternal inflation. If our universe is part of an eternally inflating multiverse, that multiverse still had to start somehow. But there are potential loopholes The BGV theorem only applies if the universe has been expanding on average. If there was a period of contraction before the expansion, or if you can construct a model where the universe is static or contracting in some regions and expanding in others in just the right way, you might be able to avoid a beginning. This brings us to cyclic models of the universe, which have a long history stretching back to ancient Hindu and Buddhist cosmologies. In modern physics, cyclic models propose that the Big Bang was not the beginning, but rather a transition from a previous contracting phase. The universe expands for billions of years, then the expansion slows, stops, and reverses. The universe contracts, getting denser and hotter until it reaches a point of maximum density, then bounces back into a new expansion phase. This cycle repeats eternally. One version of this idea is called the Big Bounce, and it's closely associated with loop quantum gravity, one of the leading approaches to quantum gravity. In classical general relativity, if you run the equations backward toward the Big Bang, you eventually reach a singularity, a point of infinite density and infinite curvature where the equations break down. But loop quantum gravity suggests that space itself is made of discrete units, quantum building blocks that can't be subdivided further, kind of like how matter is made of atoms. When you account for this graininess of space, the singularity at the Big Bang is replaced by a bounce. The universe can't contract below a certain minimum size because the quantum properties of space create a kind of pressure that pushes back. So instead of a singular beginning, you have a contracting universe that reaches a minimum size and then bounces back into expansion. In this scenario, our Big Bang was the bounce point. Before the bounce, there was a previous universe that was contracting. Before that, that universe was expanding. Before that, it was contracting from an even earlier expansion, and so on infinitely into the past. There's no beginning, no moment of creation, just an eternal cycle of expansion and contraction. The Big Bounce idea is appealing because it avoids the singularity problem and the awkward question of what caused the beginning. But it has its own problems. For one thing, loop quantum gravity is still a work in progress. It's not a complete theory yet, and the calculations involved are extraordinarily difficult. The models of a bouncing universe based on loop quantum gravity are highly simplified and might not capture the full complexity of a realistic universe. There's also the problem of entropy. The second law of thermodynamics says that entropy, roughly speaking the amount of disorder in a system, always increases over time. If the universe has been cycling forever, entropy should have already reached its maximum value, resulting in what's called heat death, a state of maximum disorder where nothing interesting can happen anymore. The fact that we exist and the universe is full of interesting structure suggests we're not at maximum entropy yet. But if the universe is infinitely old, we should have reached heat death infinitely long ago. Some cyclic models try to get around this by proposing that entropy resets at each bounce, or that the universe gets larger with each cycle, so there's always room for more entropy increase. But these are ad hoc additions that make the models less elegant and harder to test. Another famous cyclic model is Roger Penrose's conformal cyclic cosmology, or CCC. Penrose is one of the giants of theoretical physics, and his proposal is characteristically creative and mathematically sophisticated. In CCC, the universe doesn't physically contract and bounce. Instead, Penrose uses a mathematical trick called conformal rescaling. The idea is that at the very end of the universe's life, after all the stars have burned out, all the black holes have evaporated through Hawking radiation, and all that's left is a dilute gas of photons and other massless particles. The universe enters a state where the distinction between space and time becomes ambiguous. In physics, we describe events using space-time intervals, which combine space and time into a single geometric framework. Conformal rescaling is a way of stretching or shrinking the spacetime metric while preserving angles and the causal structure of events. It's like taking a map and zooming in or out. The shapes might change size, but their relative positions and orientations stay the same. Penrose proposes that this far future, cold, dilute universe can be conformally rescaled to look exactly like the hot, dense state of a new Big Bang. Mathematically, the end of one universe is identified with the beginning of the next. The universe goes through cycles called aeons, each one beginning with a Big Bang-like state and ending with a cold, dilute state that becomes the Big Bang of the next aeon. In this picture, time is infinite in both directions, but the universe is not unchanging. It cycles through aeons, each potentially lasting trillions of years. What's particularly intriguing about CCC is that Penrose claims there might be observable evidence for it. If his model is correct, events from the previous aeon could leave imprints in the cosmic microwave background of our aeon. Penrose and his collaborators have reported finding patterns in the CMB that they interpret as signatures of previous aeons, specifically concentric circles that could be the remnants of gravitational waves from colliding black holes in the previous aeon. However, most cosmologists are skeptical of these claims. The patterns Penrose found could easily be statistical flukes, and other groups have failed to find convincing evidence for them. The CCC model also requires some speculative assumptions about the far future of the universe that we can't yet verify. Still, it's a fascinating idea, and one of the few models that makes testable predictions about pre-Big Bang physics. Let's consider another approach. Instead of asking what came before the Big Bang in time, what if we ask whether there's a more fundamental level of reality from which time itself emerges? This might sound like mystical nonsense, but it's actually a serious research program in quantum gravity. In our everyday experience, time is continuous and unidirectional. It flows from past to future. We remember the past, but not the future. We can influence the future, but not the past. Time seems fundamental, more basic than space or matter. But in both quantum mechanics and general relativity, time plays a somewhat odd role. In quantum mechanics, time is a parameter, not an observable. You can't measure time itself. You measure the positions and momenta of particles, the energies of systems, and how these things change with respect to time. But time itself sits outside the quantum framework. In general relativity, time is part of the space-time fabric and can warp and bend along with space. Time can flow at different rates in different locations depending on the local gravitational field. Near a black hole, time slows down relative to far away. In some solutions to Einstein's equations, time can even loop back on itself, creating closed time-like curves where you could, in principle, travel backward in time. When physicists try to combine quantum mechanics and general relativity into a theory of quantum gravity, this peculiar role of time becomes a major problem. In the Wheeler-DeWitt equation that we mentioned earlier, which is an attempt to describe the quantum state of the entire universe, time doesn't appear as a variable at all. The equation describes a static, timeless quantum state. This has led some physicists to propose that time is not fundamental, but emergent. It arises from something deeper, something more primitive. An analogy might help. Temperature is not a fundamental property of matter. It's an emergent property that arises from the random motions of large numbers of molecules. A single molecule doesn't have a temperature. Temperature only makes sense when you have a huge collection of molecules, and it describes the average kinetic energy of that collection. Could time be similar? Could it be a macroscopic emergent property that arises from some more fundamental, timeless quantum state? If so, then asking what came before the Big Bang is like asking what's north of the North Pole, not just as an analogy, but literally. Before the Big Bang, there was a timeless quantum state from which our classical universe with its flowing time emerged. This idea is related to what's called the problem of time in quantum gravity. Different approaches to quantum gravity handle the problem of time in different ways, and each leads to a different picture of what might have existed before the Big Bang. Let's start with one of the most famous proposals, the Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in the 1980s. This is the idea that Hawking described with the North Pole analogy, and it's one of the most elegant attempts to answer the question of cosmic origins. The key insight of the Hartle-Hawking proposal is to use something called imaginary time. Now, before you check out thinking we've left the realm of real physics, imaginary time is a legitimate mathematical tool that physicists use all the time. In mathematics, imaginary numbers are numbers that involve the square root of -1, denoted by the letter I. You can't take the square root of a negative number using ordinary real numbers, so mathematicians invented imaginary numbers to handle this situation. And it turns out that imaginary numbers are incredibly useful in physics, particularly in quantum mechanics. In the Hartle-Hawking model, when you go back toward the Big Bang using ordinary real time, you eventually reach a point where the classical notion of time breaks down. But if you switch to imaginary time, something remarkable happens. The distinction between time and space disappears. In the imaginary, time formulation, what we call the moment of the Big Bang, transforms into a smooth, round, four-dimensional surface with no boundaries and no singularities. It's like the surface of a sphere. If you're standing on Earth and you walk south, you'll eventually reach the South Pole. When you get there, you can't go any further south because every direction from the South Pole is north. But nothing special happens at the South Pole. There's no edge, no boundary, no beginning. It's just a smooth continuation of the surface. Similarly, in the Hartle-Hawking model, if you go back in imaginary time toward the Big Bang, you reach a point analogous to the South Pole. You can't go any further back, not because there's a boundary or a singularity, but because the notion of going back ceases to make sense. Time smoothly transforms into a space-like dimension. The universe has no boundary in imaginary time, hence the name no-boundary proposal. Now, you might be wondering, what does imaginary time actually mean physically? This is where things get philosophically tricky. Hawking and Hartley argued that only imaginary time is really real, in a sense. Real time, the time we experience in our everyday lives, is something that emerges from the more fundamental imaginary time description. When the universe is very small and quantum effects dominate, you have to use imaginary time to describe it properly. As the universe expands and classical physics takes over, imaginary time transitions into real time, and we get the flowing, directional time that we're familiar with. In this picture, asking what happened before the Big Bang is indeed like asking what's north of the North Pole. There is no before because the concept of before only makes sense in real time. And real time only exists after the universe has emerged from its quantum state. The universe doesn't have a beginning in the sense of a first moment in time. It simply exists as a complete, self-contained, four-dimensional object with no boundaries. The Hartle-Hawking proposal is mathematically beautiful, but it's not without problems. For one thing, it requires making some choices about how to do the quantum mechanical calculations, choices that are somewhat arbitrary and lead to different results. It also makes predictions that don't match our observations particularly well. The model tends to predict a universe that's much smaller and simpler than the one we actually see. There have been various attempts to modify the proposal to fix these issues, but none have been entirely successful. Another issue is that the whole notion of a quantum state of the universe is philosophically problematic. In ordinary quantum mechanics, we describe particles or systems with wave functions, and we interpret these wave functions using the Born rule, which says that the square of the wave function gives you the probability of finding the particle in a particular state when you measure it. But if you're talking about the wave function of the entire universe, who's doing the measuring? Where is the observer standing who's outside the universe looking in? This is a deep problem in quantum cosmology that we don't have a fully satisfactory answer to. Some physicists argue we need to modify our interpretation of quantum mechanics to handle this situation, perhaps by adopting something like the many-worlds interpretation, where all possible outcomes of quantum measurements actually occur in separate branches of reality. But we're getting ahead of ourselves. Let's look at another approach to the question of what came before the Big Bang, one that takes us back to the idea of eternal inflation, but adds some interesting twists. As we discussed earlier, if inflation is driven by a quantum field subject to quantum fluctuations, it might never completely end everywhere. This leads to the picture of eternal inflation creating a multiverse of pocket universes. But where did the inflating region come from in the first place? One possibility, again proposed by Alexander Vilenkin, is that the inflating region tunneled into existence from nothing via quantum mechanics. But there's another possibility that's worth considering. What if our inflationary period was triggered by the end of a previous universe? This is the idea behind several models that combine inflation with cyclic or bouncing cosmologies. In these models, a previous universe underwent gravitational collapse, but instead of forming a singularity, quantum effects caused it to bounce back into expansion. This bounce naturally creates the conditions for inflation because the bounce releases an enormous amount of energy that can drive rapid expansion. So our Big Bang was both an end and a beginning, the death of one universe and the birth of another. One specific version of this idea comes from string theory, which is probably the most well-known approach to quantum gravity, though also one of the most controversial. String theory proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings of energy. Different vibration patterns correspond to different particles. An electron is one vibration pattern, a quark is another, a photon is another, and so on. For string theory to be mathematically consistent, it requires extra dimensions of space beyond the three we're familiar with. Depending on which version of string theory you're working with, you need either 10 or 11 total dimensions. The extra dimensions are supposedly curled up or compactified at incredibly small scales, which is why we don't notice them in everyday life. Now, string theory has had remarkable mathematical successes. It naturally includes gravity, which is represented by a particular vibration pattern of strings. It unifies all the forces of nature into a single framework, and it makes finite, sensible predictions in situations where other approaches to quantum gravity break down. But string theory also has some serious problems. For one thing, it's not really a single theory, but a vast landscape of possible theories. Depending on how you curl up the extra dimensions, you get different physics in the remaining dimensions. Current estimates suggest there might be 10 to the 500 or more different possible versions of string theory, each giving rise to a different set of physical laws and constants. This is called the string theory landscape, and it's both a blessing and a curse. It's a blessing because it provides a potential explanation for why our universe has the particular laws and constants it does. With so many possibilities, maybe all of them exist somewhere in the multiverse, and we happen to find ourselves in one that can support life. But it's also a curse because with so many possibilities and no way to calculate which one we should be in, string theory loses much of its predictive power. You can't use it to make definite predictions about what we should observe, because almost any observation could be accommodated by choosing the right version of the theory from the landscape. Some string theorists have tried to turn this problem into a feature by combining the landscape with eternal inflation. In this picture, eternal inflation constantly creates new pocket universes, and each pocket universe might realize a different point in the string theory landscape. Each pocket has different physical laws, different constants, different particles. Our universe is just one pocket among an unfathomable number of others. This leads naturally to the anthropic principle, which we need to talk about because it comes up again and again in discussions of what came before the Big Bang. The anthropic principle, in its weak form, simply states that we should not be surprised to find ourselves in a universe that's capable of supporting life, because if the universe couldn't support life, we wouldn't be here to observe it. This might sound tautological, but it can actually be a useful scientific principle. For example, suppose you're wondering why Earth is at just the right distance from the Sun for liquid water to exist on its surface. One answer is that there are billions of planets in the galaxy at various distances from their stars, and we necessarily find ourselves on one of the planets where conditions are right for life. We don't need to invoke any special fine-tuning or divine intervention to explain this. It's just selection bias. The strong anthropic principle goes further and suggests that the universe must have properties that allow life to develop, because if it didn't, there would be no observers, and a universe without observers somehow doesn't fully exist or doesn't count. This version is much more philosophically controversial and starts to sound less like science and more like metaphysics. But even the weak anthropic principle becomes problematic when applied to the multiverse. If there are infinitely many universes with all possible laws of physics, then somewhere out there is a universe exactly like ours, except you're wearing a different color shirt. Somewhere else is a universe where dinosaurs never went extinct. Somewhere else is a universe where the laws of physics are so different that matter as we know it can't exist. With infinite possibilities, everything that can happen does happen. And once you accept that, the anthropic principle seems to lose its explanatory power. You can explain anything by saying, well, somewhere in the multiverse, it had to happen. Many physicists find this deeply unsatisfying. Physics is supposed to make predictions, to tell us what will happen in a given situation. But if the multiverse picture is correct, the best we can do is calculate probabilities over the distribution of possible universes, and even that requires making assumptions about how to count universes, which turns out to be extraordinarily difficult. This is called the measure problem in eternal inflation, and it's one of the biggest challenges facing the theory. Nevertheless, some version of the multiverse seems to arise naturally from several independent lines of reasoning. Eternal inflation suggests it. String theory's landscape suggests it. The many worlds interpretation of quantum mechanics suggests it. And some approaches to quantum cosmology, like the Hartle-Hawking no-boundary proposal, also lead to a multiverse of sorts. It's hard to know whether this convergence means we're onto something real, or whether it's an artifact of our current incomplete understanding. Let's consider another completely different approach to pre-Big Bang physics, one that comes from loop quantum gravity. As mentioned earlier, loop quantum gravity proposes that space itself is made of discrete quantum units, often visualized as a kind of quantum foam or spin network. In this picture, space-time is not smooth and continuous at the smallest scales, but has a granular structure. When you apply loop quantum gravity to cosmology, something interesting happens at the Big Bang. Instead of a singularity where density and curvature become infinite, you get a bounce. The quantum properties of space create a repulsive force that prevents the universe from collapsing to a point. The universe contracts down to a minimum size, roughly on the order of the Planck scale, and then bounces back into expansion. Our Big Bang is this bounce. Before the bounce, there was a previous universe that was contracting. Crucially, this previous universe was not identical to ours. During the contraction phase, the universe would have been very different from the expanding universe we see today. Time would still flow forward, not backward. The arrow of time doesn't reverse during contraction because the thermodynamic arrow of time, which is based on the increase of entropy, doesn't depend on whether space is expanding or contracting. One of the appealing features of loop quantum cosmology is that it makes definite, falsifiable predictions. The bounce leaves an imprint on the cosmic microwave background radiation that's different from what standard inflation predicts. We haven't seen evidence for this signature yet, which places constraints on the model, but it's the kind of prediction that could be tested with future observations. That's more than you can say for many other approaches to quantum gravity. However, loop quantum gravity also has its limitations. The full theory is incredibly mathematically complex, and most calculations have only been done for highly simplified toy models. It's not yet clear whether the bounce picture survives when you include all the complications of a realistic universe with matter, radiation, and all the different quantum fields we observe. There's also the question of what happens in the contracting phase before the bounce. If you keep running the equations backward, do you reach another bounce? Is it bounces all the way down, an infinite regress of expansions and contractions? Or is there some other boundary condition? Some loop quantum cosmologists have argued that the theory naturally leads to a cyclic universe with infinite bounces extending into the past and future. Others suggest there might be a beginning after all, perhaps a first bounce that emerged from some kind of quantum state. The jury is still out. Another fascinating approach comes from a causal set theory, which takes the idea that space-time might be discrete to an extreme. In causal set theory, space-time is not a smooth continuum, but a collection of discrete points or events. The only structure these points have is their causal relationships, which events are in the past light cone of which other events. From this minimal structure, the continuous spacetime we experience is supposed to emerge in some averaged or coarse-grained sense, kind of like how a digital photograph is made of discrete pixels but looks smooth when you zoom out. If causal set theory is correct, then asking what happened before the Big Bang might be like asking what happened before the first frame of a movie. There's no before. The universe is a discrete sequence of events, and the Big Bang corresponds to the earliest events in the sequence. Time itself is discrete, made of indivisible moments, and there simply aren't any moments before the first one. This sounds appealingly clean and simple, but causal set theory faces enormous technical challenges. Nobody has yet figured out how to extract predictions about observable physics from the theory, and it's not even clear that general relativity emerges from causal sets in the right way. It remains a speculative research program with a lot of work still to do. Let's turn our attention now to an idea that's more speculative, but also more radical than anything we've discussed so far. What if the Big Bang was the result of a collision between higher dimensional objects called brains? This idea comes from a particular approach to string theory and leads to what's called the equiperiodic universe scenario. In string theory, as we mentioned, there are extra dimensions of space beyond the three we're familiar with. Some versions of string theory also include extended objects, called branes, short for membranes. A brane is like a higher dimensional surface. A zero brane is a point, a one brane is a string, a two brane is a surface like a sheet of paper, and so on. Our entire universe, with its 3 dimensions of space and 1 of time, might actually be a 3 brane embedded in a higher dimensional space. We're stuck on this brane like ants crawling on a sheet of paper, unaware of the directions perpendicular to the paper. Now, if our universe is a brane, there might be other branes floating around in the higher dimensional space. Normally, these branes don't interact much. The various forces we're familiar with, electromagnetism and the nuclear forces, are confined to our brane. But gravity is different. Gravity can propagate through the extra dimensions, which is why it might be much weaker than the other forces. The gravitational force is diluted by spreading out into the extra dimensions. Every so often in this picture, 2 branes might collide. When they do, an enormous amount of energy is released. This collision could be what we call the Big Bang. The universe didn't begin from a singularity, but from the collision of our brain with another brain. After the collision, the brains bounce apart, and the energy from the collision thermalizes into the hot, dense state we associate with the early universe. This is the ekpyrotic scenario, named after the ancient Stoic idea of ekpyrosis, a periodic conflagration that destroys and recreates the universe. In some versions of this model, the collisions happen periodically. The brains attract each other, collide, bounce apart, are gradually pulled back together by gravity, collide again, and so on. Each collision is a Big Bang, and the cycle repeats eternally. The ekpyrotic model is intriguing because it provides a concrete mechanism for what triggered the Big Bang and potentially explains some features of the universe that are otherwise hard to understand. For example, the model can generate the density fluctuations we see in the cosmic microwave background without requiring inflation, though most versions still include a brief period of inflation after the collision to solve other cosmological problems. However, the ekpyrotic scenario faces significant challenges. For one thing, it requires string theory to be correct, and as we've discussed, string theory remains unproven. It also requires a very specific configuration of brains and extra dimensions, and it's not clear why the universe should have this configuration rather than some other one. The model makes some predictions about the cosmic microwave background that are different from standard inflation, particularly regarding gravitational waves, but so far observations haven't been precise enough to distinguish between the models definitively. One of the most recent and radical ideas about what came before the Big Bang comes from theoretical physicist Lee Smolin and his colleagues, who proposed something called cosmological natural selection. This is a truly wild idea that treats universes like biological organisms that reproduce and evolve. Here's how it works. When a black hole forms in our universe, the matter falling into it gets crushed to incredible densities. In classical general relativity, this matter collapses to a singularity, a point of infinite density. But if we take quantum gravity seriously, the singularity might be replaced by a bounce, similar to what happens at the Big Bang in loop quantum cosmology. Smolin proposes that this bounce doesn't happen inside our universe. Instead, it spawns a new universe that buds off from ours through the black hole. From our perspective, the matter falls into the black hole and disappears. But from the perspective of observers in the new universe, assuming there are any, their universe begins with a Big Bang-like event. The new universe is causally disconnected from ours. It has its own space and time. But crucially, it inherits physical constants and laws that are similar to our universe but not identical. There are small random variations, like mutations in biology. Now, if some combinations of physical constants are more likely to produce black holes than others, then universes that produce lots of black holes will have lots of offspring universes, while universes that produce few black holes will have few offspring. Over many generations, the population of universes will evolve toward configurations that maximize black hole production. This is natural selection applied to cosmology. Smolin argues that our universe looks the way it does because it's descended from a long line of universes that were good at making black holes. The constants of nature are fine-tuned, not by design or by luck, but by a kind of evolutionary process. Universes that don't make black holes don't leave offspring and die out of the population. It's a fascinating idea, but it's also highly speculative and very difficult to test. The prediction is that our universe should be close to optimal for black hole production. But calculating what optimal means requires knowing a lot about the physics of black hole formation and making small changes to the constants of nature in ways we can't test experimentally. Some physicists love cosmological natural selection for its creativity and its attempt to explain fine-tuning without invoking the anthropic principle. Others dismiss it as untestable speculation that's not really science. The truth probably lies somewhere in between. What all of these theories have in common is that they're attempts to apply quantum mechanics to the problem of the Big Bang singularity. They all say, in one way or another, that when you properly account for quantum effects, the singularity goes away and is replaced by something else. A bounce, a tunneling event, a smooth transition, a collision, whatever. The singularity is an artifact of using classical physics in a regime where classical physics doesn't apply. But there's a deeper issue lurking here that we need to address, and it brings us back to one of the most fundamental and strange features of quantum mechanics. In quantum mechanics, systems don't have definite properties until they're measured. Before measurement, a particle doesn't have a definite position or momentum. It exists in a superposition of all possible positions and momenta simultaneously. Only when you measure it does the wave function collapse, and the particle suddenly has a definite value. This is the famous measurement problem of quantum mechanics, and it's been debated since the theory was first developed in the 1920s. Different interpretations of quantum mechanics handle this differently. The Copenhagen interpretation says that measurement causes the wave function to collapse, but doesn't specify what counts as a measurement or why measurement should have this special role. The many worlds interpretation says the wave function never collapses. Instead, every possible outcome of a measurement actually occurs, but in separate branches of reality. When you measure a particle's position, the universe splits into multiple copies, one for each possible outcome, and you only experience one branch. Other interpretations, like pilot wave theory or objective collapse theories, propose different solutions. But here's the problem when you're talking about the entire universe. If the universe is described by a quantum wave function, and that wave function represents a superposition of different possible states, when does it collapse? Who or what is measuring the universe? You can't have an observer outside the universe measuring it because there is no outside. This is sometimes called the quantum measurement problem for cosmology, and it's a serious conceptual difficulty. One response is to say that we need to modify quantum mechanics when applying it to cosmology. Maybe the wave function of the universe doesn't collapse. Maybe it just is. We exist within one particular branch or one particular configuration, but the wave function describes all possibilities at once. This is essentially the many worlds view applied cosmologically. Every possible history of the universe exists in superposition, and we experience one particular history. But this raises bizarre questions. In the Hartle-Hawking no-boundary proposal, for instance, the wave function of the universe is supposed to give probabilities for different possible universes with different properties. But probabilities relative to what? If you're inside the wave function, you can't step outside and sample different universes to see how often each one occurs. Some physicists, like Don Page and others, have argued that we should interpret the wave function of the universe using something called the epistemic interpretation, where the wave function doesn't represent objective reality, but rather our state of knowledge or information about reality. But this seems to beg the question because if we're part of the universe, our knowledge is part of the universe too. How can our knowledge determine what the universe is? These are deep philosophical problems that physicists are actively grappling with, and there's no consensus on the answers. What this suggests is that we might need a more radical rethinking of quantum mechanics itself when applying it to cosmology. Or perhaps we need to rethink what we mean by the universe. Let's explore another angle on this question by thinking about information and entropy. One of the most profound insights from 20th century physics is that information is physical. It's not some abstract thing separate from the material world. Information has entropy. It takes energy to erase information, and the information content of a region of space is limited by its surface area, not its volume. This last point is particularly strange and leads to what's called the holographic principle. the holographic principle emerged from studying black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy proportional to the area of their event horizon, not their volume. This was surprising because entropy is usually thought of as counting the number of possible microscopic states of a system, and you'd expect that number to scale with volume. The more space you have, the more states you can fit. But for black holes, it scales with area. This led physicists to conjecture that the maximum amount of information that can be contained in any region of space is determined by the area of its boundary, measured in Planck units. It's as if the three-dimensional reality we perceive is actually encoded on a two-dimensional surface, like a hologram. Now, what does this have to do with what came before the Big Bang? Well, if information is fundamental, and if the universe has a finite information content, then maybe the Big Bang was not the creation of something from nothing, but rather a transformation or reorganization of pre-existing information. Some physicists have speculated that there might be a more fundamental informational or computational substrate underlying physical reality, and that the Big Bang represents a transition in this substrate. This is related to ideas in digital physics and the simulation hypothesis, though most physicists are careful to distance themselves from the more pop culture versions of these ideas. The basic notion is that physical laws might be computational rules operating on information, and what we call matter and energy are patterns of information evolving according to these rules. If this is true, then asking what came before the Big Bang is like asking what was running on a computer before you started a particular program. Well, maybe the computer was off, in which case there was no before. Or maybe the computer was running a different program, in which case the previous program is analogous to a previous universe or a pre-Big Bang state. Or maybe the computer was always on, running an infinite sequence of programs, and our universe is just the current one. These analogies break down quickly, of course, because we don't actually think the universe is a computer simulation in the literal sense. But they point toward a possible conceptual framework where the Big Bang is a transition between different modes or states of a more fundamental informational structure. There's also the question of what role entropy plays in all of this. As mentioned earlier, the second law of thermodynamics says that entropy always increases over time. This is arguably the most fundamental arrow of time we have. It's why we remember the past but not the future, why eggs scramble but don't unscramble, why heat flows from hot to cold and not the reverse. But the early universe, just after the Big Bang, was in a state of extremely low entropy. Everything was smooth and uniform, as we can see from the cosmic microwave background. There were tiny fluctuations, but overall it was remarkably ordered. As the universe expanded and evolved, structure formed. Galaxies, stars, planets, life, all of this represents an increase in local order, but it comes at the cost of a greater increase in entropy elsewhere. Stars burn hydrogen into helium and radiate energy into space, increasing the overall entropy of the universe. So, here's the puzzle. If the universe started in a low entropy state, and entropy has been increasing ever since, why did it start in such a special low entropy state? This is called the past hypothesis, or the problem of cosmological initial conditions. A generic initial state would have much higher entropy. In fact, the most probable state for the universe is thermal equilibrium, maximum entropy, where nothing interesting happens. The fact that we're in a low entropy state that's evolving toward higher entropy requires explanation. One answer is to say that the initial conditions of the Big Bang were just set that way, and we don't need to explain it further. But this feels unsatisfying. It's not much different from saying God made it that way. Another answer comes from inflation. Inflation naturally produces a low entropy state because the inflating region starts in a very special configuration dominated by the energy of the inflatant field. When inflation ends and this energy converts to matter and radiation, you get a hot, smooth, low-entropy universe. But this just pushes the question back. Why did the inflating region start in that particular state? If inflation is eternal and creates infinitely many pocket universes, most of them won't have low entropy. So, why do we find ourselves in one of the special low-entropy pockets? This is where the anthropic principle rears its head again. Maybe only low-entropy universes can support life and observers, so we necessarily find ourselves in one. But many physicists find this deeply unsatisfying. There's a more radical possibility proposed by cosmologist Sean Carroll and others, which is that the low entropy of the Big Bang is not a feature that needs explaining, but rather an artifact of our limited perspective. If the universe is much larger than the observable region we can see, and if different regions have different entropy, then we would necessarily find ourselves in a region where entropy started low, because only those regions can support observers. This works if the universe is spatially infinite and eternal inflation is true. Most of the universe is in a high entropy state, but rare fluctuations create low entropy pockets, and we're in one of those pockets. The Big Bang, in this view, is not the beginning of everything, but just the beginning of our local low entropy region. Another possibility is that entropy can decrease in a bouncing or cyclic universe if the universe gets bigger with each cycle. If each bounce produces a universe larger than the previous one, there's more room for entropy to spread out, so the entropy per unit volume can decrease even as the total entropy increases. This allows for an arrow of time that persists through the bounce. But these models require very specific conditions and fine-tuning to work, which makes them feel somewhat ad hoc. Let's shift gears and talk about what we might actually be able to observe that could tell us something about pre-Big Bang physics. This is crucial because without observational tests, all these theories remain mathematical speculation rather than science. The cosmic microwave background radiation is our best window into the early universe. It's a snapshot of the universe when it was only 380,000 years old. By studying the tiny temperature fluctuations in the CMB, we can learn about the conditions at even earlier times, potentially all the way back to the inflationary epoch. Different models of what happened before or during the Big Bang make different predictions about the pattern of these fluctuations. For example, standard inflation predicts that the fluctuations should be nearly scale invariant, meaning they have roughly the same amplitude at all scales, with a slight tilt. And that's what we observe. But some pre-Big Bang models, like the ekpyrotic scenario or certain cyclic models, predict a different tilt or different patterns in the fluctuations. So far, the observations favor standard inflation, but they don't rule out all alternatives. Another key observable is gravitational waves. Just as electromagnetic radiation can travel across the universe, so can gravitational radiation, ripples in the fabric of spacetime itself. Inflation should have generated a background of primordial gravitational waves, and detecting these would be a major confirmation of the theory. Moreover, different models make different predictions about the amplitude and spectrum of these gravitational waves. The ekpyrotic model, for instance, predicts far weaker primordial gravitational waves than standard inflation. Loop quantum cosmology makes predictions about features in the gravitational wave spectrum that could distinguish a bounce from a singular beginning. Several experiments are currently searching for these primordial gravitational waves, either by looking for a particular pattern in the polarization of the cosmic microwave background, or by directly detecting gravitational waves with space-based interferometers. So far, no conclusive detection has been made, but technology is improving rapidly. If we do detect primordial gravitational waves, and if we can measure their properties precisely, we might be able to distinguish between different scenarios for what happened at or before the Big Bang. There's also the possibility of finding other signatures in the CMB. Roger Penrose, as mentioned earlier, has claimed to find concentric circles in the CMB that he interprets as evidence for his conformal cyclic cosmology. Most cosmologists are skeptical, arguing that the patterns are consistent with random chance, but Penrose continues to refine his analysis. If he's right, it would be revolutionary. We'd have direct observational evidence of events from a previous aeon, from before our Big Bang. Similarly, some models predict that there should be anomalies or features in the CMB at the largest scales that reflect the geometry or quantum state of the pre-Big Bang universe. There are some puzzling observations, like the fact that the CMB has less power at large angular scales than predicted, and that there seem to be some preferred directions in the sky, which violates the assumption that the universe should look statistically the same in all directions. These anomalies are not very statistically significant, and they might just be flukes, but they've inspired a lot of theoretical speculation about whether they might be telling us something about pre-Big Bang physics. Another possible source of information comes from the distribution of galaxies and large-scale structure in the universe. The same density fluctuations that show up in the CMB also seeded the formation of galaxies and clusters of galaxies. By mapping out the three-dimensional distribution of galaxies across cosmic history, we can test models of the early universe in complementary ways to CMB observations. Some pre-Big Bang scenarios make predictions about features in the matter-power spectrum that might be detectable with future surveys. There's also the intriguing possibility that we might detect cosmic strings or other topological defects. These are hypothetical structures that could have formed during phase transitions in the early universe, kind of like cracks in ice when water freezes. Different models of the Big Bang predict different numbers and types of topological defects. If we found them, they could provide clues about the conditions at the Big Bang and possibly before. Cosmic strings would produce distinctive patterns in the CMB, and could also be detectable through their gravitational lensing effects. So far, no cosmic strings have been found, but searches continue. Looking even further ahead, there's the possibility of detecting primordial black holes. These are black holes that formed in the very early universe, not from the collapse of stars, but from the direct collapse of dense regions. If primordial black holes exist, and if some of them are small enough, they could be evaporating right now through Hawking radiation, producing detectable signals. The distribution and properties of primordial black holes depend sensitively on the conditions during and shortly after the Big Bang, so finding them could teach us a lot. Some physicists have even speculated that primordial black holes could be the dark matter, the mysterious invisible substance that makes up about 85% of the matter in the universe. If that's true, then understanding primordial black holes becomes even more important, and it links the question of what happened at the Big Bang to one of the biggest mysteries in contemporary cosmology. But we should be honest about the limitations here. Even with the best observations we can imagine, there's a limit to how far back we can see. The cosmic microwave background is a wall we can't see past directly, because before the CMB was emitted, the universe was opaque to light. Gravitational waves can penetrate further back, potentially all the way to the inflationary epoch, but even they have limits. If we want to probe the Planck era, the first 10 to the negative 43 seconds when quantum gravity effects were dominant, we're going to need indirect methods. We'll have to look for signatures that propagated forward from that era into later times when we can observe them. And there's no guarantee such signatures exist or that they're detectable. This brings us to an uncomfortable truth. It's possible that the question of what came before the Big Bang is fundamentally unanswerable by science. Not because we're not smart enough, or because our technology isn't good enough, but because the information we'd need to answer the question simply doesn't exist in the observable universe. It was destroyed or scrambled by the extreme conditions of the Big Bang itself. If that's the case, We might be able to construct multiple different theories that all match every observation we can possibly make, but we'll never be able to determine which one is actually true. This is sometimes called underdetermination of theory by evidence, and it's a recognized issue in philosophy of science. When you have multiple theories that make identical predictions about everything observable, science can't tell you which one is right. You might have to resort to other criteria like simplicity, elegance, or philosophical preference. Some physicists are comfortable with this. They argue that science is about explaining observations, not about uncovering some ultimate metaphysical truth about reality. If two theories make the same predictions, they're equivalent for scientific purposes, even if they tell very different stories about what's really going on. Other physicists find this deeply troubling. They got into physics to understand how reality actually works, not just to fit curves to data. They want to know what really happened at the Big Bang, what really came before, if anything, what the universe is really made of at the deepest level. This tension between different conceptions of what science is for, what questions it can answer, is very much alive in contemporary cosmology. It's particularly acute when discussing the multiverse. If eternal inflation is true, there are infinitely many pocket universes with different properties, and most of them are forever beyond our ability to observe. They're causally disconnected from us. Light from them can never reach us, and we can never reach them. So, in what sense do they exist? Is it meaningful to talk about their existence if they're fundamentally unobservable? Some physicists say yes. If a theory makes predictions about things we can observe, and those predictions are confirmed, and the theory also predicts the existence of other unobservable things, then we should believe those things exist. This is called inference to the best explanation. We can't observe quarks directly either, but we believe they exist because quantum chromodynamics, the theory that includes quarks, makes predictions about things we can observe, like the behavior of protons in particle accelerators, and those predictions are confirmed. Other physicists say no. They argue that science should only make claims about observable quantities. Theories should be formulated in terms of what we can measure, and we shouldn't believe in entities that are in principle unobservable, no matter how mathematically convenient or explanatorily powerful they might be. This debate intersects with questions about what came before the Big Bang, because many of the theories we've discussed involve entities or events that are, at least with our current understanding, forever beyond the reach of observation. The quantum state from which the universe tunneled in Vilenkin's model, the previous contracting universe before the bounce-in-loop quantum cosmology, the other branes in the ekpyrotic scenario, the previous aeons in Penrose's conformal cyclic cosmology. Are these scientifically legitimate ideas, or are they metaphysical speculation dressed up in mathematical clothing? There's no easy answer, and different scientists draw the line in different places. What we can say with confidence is that the question of what came before the Big Bang pushes science to its absolute limits, and maybe beyond. It forces us to confront the deepest assumptions we make about reality, about time, about causation, about what it means for something to exist. And interestingly, many of the proposals we've discussed end up converging on similar philosophical territory despite taking very different mathematical routes to get there. They suggest that our intuitive notions of time and causation, which work perfectly well in everyday life and even in most areas of physics, break down when you try to apply them to the universe as a whole. Time might not be fundamental. It might emerge from something deeper. Or it might be circular or branching rather than linear. Causation might not require a temporal sequence of cause followed by effect. The universe might be self-causing in some sense, or it might simply exist as a brute fact that doesn't require an explanation. These ideas are strange and counterintuitive, but then again, so is most of modern physics. Quantum mechanics tells us that particles can be in multiple places at once, and that measuring one particle can instantaneously affect another one across the galaxy. General relativity tells us that time flows at different rates depending on how fast you're moving and how deep you are in a gravitational field. We've learned to accept these things because the mathematics works and the predictions are confirmed by experiments. Maybe we need to extend that same willingness to accept strangeness when thinking about cosmic origins. Let's consider what all of this might mean for the far future of the universe, because the question of what came before is intimately connected to the question of what comes after. If the universe emerged from a quantum vacuum or tunneled from nothing, could it tunnel back to nothing? If our Big Bang was a bounce from a previous contracting universe, will there be another bounce in the future? The answer depends on what the universe is made of and how its expansion is behaving. For most of the 20th century, cosmologists expected that the expansion of the universe would eventually slow down due to gravity and either reverse into a contraction or asymptotically approach zero expansion. But in 1998, observations of distant supernovae revealed something shocking. The expansion of the universe is not slowing down, it's speeding up. This accelerating expansion is attributed to something called dark energy, which appears to be a property of space itself. The more space there is, the more dark energy there is, which pushes the expansion even faster, creating more space, which creates more dark energy in a runaway feedback loop. If dark energy remains constant, which is what current observations suggest, the universe will continue expanding forever at an ever-increasing rate. In the far future, galaxies outside our local group will recede beyond our cosmic horizon, disappearing from view. Eventually, stars will burn out, black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy called heat death. Everything will be cold, dark, and dilute, with no energy gradients left to power any interesting processes. This is a depressing picture, sometimes called the Big Freeze. But it's not the only possibility. If dark energy is not constant but instead increases over time, the expansion could accelerate so rapidly that it rips apart galaxies, stars, planets, and eventually even atoms. This is called the Big Rip, and it would bring the universe to a rather violent end in a finite amount of time. On the other hand, if dark energy decreases over time, or if it eventually becomes negative, gravity could win and the expansion could reverse. The universe would enter a contracting phase, getting denser and hotter, eventually approaching a big crunch that might be followed by a big bounce and a new cycle of expansion. Current observations don't tell us which of these scenarios will occur. The nature of dark energy is one of the biggest unsolved problems in physics. We've measured that it exists and that it's causing accelerated expansion, but we don't know what it is or how it will behave in the future. If we're living in a false vacuum, as some particle physics models suggest, there's another possibility. The vacuum could decay to a lower energy state. This would happen through quantum tunneling, with a bubble of true vacuum forming somewhere and expanding at the speed of light. Everything the bubble encounters is converted to the new vacuum state with different physical constants and laws. From our perspective, it would be the end of the universe as we know it, though from the perspective of observers in the new vacuum, if any could exist there, it would be a new beginning. This vacuum decay could happen tomorrow or in a trillion years. We have no way of predicting when because it's a quantum mechanical process that's inherently probabilistic. Some calculations suggest our vacuum is stable. Others suggest it's metastable, meaning it's stable enough to last for an extraordinarily long time but not forever. There's even the disturbing possibility that our vacuum is on the edge between stability and instability, which would explain why the Higgs boson mass and other properties of the universe have the particular values they do. If this is true, we're living in what some physicists call the most dangerous possible universe, where vacuum decay is unlikely but not impossible. Roger Penrose's conformal cyclic cosmology offers a different vision of the far future. In his model, the heat-death state with maximum entropy is conformally equivalent to a new Big Bang. The end of one aeon seamlessly becomes the beginning of the next. Time continues infinitely, but the universe goes through cycles, each one potentially lasting trillions upon trillions of years. From this perspective, our Big Bang was not the beginning, but merely one in an infinite sequence of beginnings. If Penrose is right, the universe is eternal in both directions. There was no first aeon, and there will be no last one. It's an appealing vision in some ways, because it avoids the discomforting notion of a beginning from nothing or an end in oblivion. But it raises its own questions. Why these cycles? Why this particular conformal structure? And how does information or structure propagate from one aeon to the next? The ekpyrotic scenario and other brane collision models suggest that the cycles involve collisions between branes in a higher dimensional space, with each collision sparking a new Big Bang. In these models, the future might involve our brain colliding with another brain, which would be catastrophic from our perspective, but would spawn new universes from the debris. These collisions could be periodic or random, depending on the dynamics of the higher dimensional space. The eternal inflation picture offers yet another perspective. If inflation is eternal into the future, then the multiverse will continue spawning new pocket universes forever. Our particular pocket will eventually reach heat death, but countless other pockets are being born all the time, each with their own Big Bangs. From the perspective of the multiverse as a whole, there's no end, just an eternal branching tree of universes. But observers in any particular pocket, like us, experience a beginning and an end. This raises fascinating questions about the nature of existence and identity. If the multiverse is eternal and infinite, with all possible universes existing somewhere, then every possible version of you exists. There are versions of you where you made different choices, versions where historical events unfolded differently, versions where the laws of physics are slightly different. In some sense, everything that can happen does happen, infinitely many times. Some philosophers and physicists find this picture liberating. It removes the need for an ultimate explanation or purpose. Things are the way they are because all possible ways exist. Others find it nihilistic. If everything happens, nothing is special. Your choices don't matter because every possible choice is realized somewhere. Of course, this logic is flawed because your choices absolutely matter to you in this particular branch of the multiverse. But the philosophical implications are dizzying. Let's return to the question of whether physics can ever truly explain why there is something rather than nothing. We've seen that physics can potentially explain how a universe can come from a quantum vacuum through tunneling, or how it can emerge from a more fundamental timeless state, or how it can be eternal with no beginning. But all of these explanations presuppose something. They presuppose the existence of quantum mechanics, or the existence of some set of physical laws, or the existence of a mathematical structure. Can physics explain why these things exist? This is where we hit what might be called the ultimate regress. If you explain A in terms of B, you can then ask why B exists. If you explain B in terms of C, you can ask why C exists. At some point, you either reach something that can't be explained further, a brute fact that simply is, or you find yourself in a circular explanation where A explains B, B explains C, and C explains A. Some philosophers argue that this regress is unavoidable and that there must be something that exists necessarily without explanation. In classical philosophy and theology, this necessary being is often identified with God. But you could also identify it with the laws of physics, or with mathematics, or with some other abstract structure. The point is that at the bottom of any explanatory chain, there has to be something that grounds everything else. Others argue that the regress can be circular without being vicious. Maybe the universe is self-explaining in some sense. The laws of physics give rise to the universe, and the universe gives rise to the laws of physics. This sounds paradoxical from a temporal perspective, but if time is not fundamental, maybe it makes sense. There's also the possibility that the question itself is confused. Maybe asking why something exists rather than nothing is like asking why 1 + 1 = 2. It's not a question that admits an answer because it's based on a misunderstanding of what existence is. This is related to ideas in modal logic and the philosophy of metaphysics that are frankly beyond my expertise and probably beyond the scope of what we can meaningfully discuss without getting hopelessly tangled in philosophical jargon. What we can say is that the question has troubled philosophers and theologians for thousands of years, and the fact that physicists are now engaging with it seriously, using mathematics and attempting to connect it to observations, represents progress of a sort. Even if we can't answer the question definitively, we've clarified what the question means, what assumptions it rests on, and what kinds of answers are possible in principle. That's not nothing. Let's talk about what future observations might tell us. The next generation of cosmic microwave background experiments, with names like CMB-S4 and LIGHTBIRD, will measure the polarization of the CMB with unprecedented precision. If primordial gravitational waves exist at the level predicted by many inflation models, these experiments should detect them. That would be a major confirmation of inflation and would rule out some alternatives like the equiparodic model. Even if they don't detect primordial gravitational waves, the non-detection would place tight constraints that could rule out certain inflation models. Similarly, upcoming surveys of galaxies and large-scale structure, like the Vera Rubin Observatory and the Euclid Space Telescope, will map the distribution of matter in the universe with exquisite detail. This will allow us to test models of the early universe in new ways, and potentially detect subtle signatures of pre-Big Bang physics. Further in the future, space-based gravitational wave detectors like LISA will be able to detect lower-frequency gravitational waves than current ground-based detectors. These could potentially include primordial gravitational waves or signals from cosmic strings or other exotic phenomena. If we're lucky, we might even detect signals from phase transitions or other events in the very early universe. There's also the possibility of detecting particles from the early universe directly. The universe should be filled with a cosmic neutrino background, analogous to the cosmic microwave background but made of neutrinos instead of photons. These neutrinos decoupled from other matter even earlier than the photons that make up the CMB when the universe was only about 1 second old. Detecting these relic neutrinos would be incredibly difficult because they have very low energies and interact very weakly with matter. But several experiments are attempting it, and a detection would open a new window on the early universe. If there are other light particles that were abundant in the early universe but that we haven't discovered yet, they might also have left a relic background that we could detect. Some models of dark matter predict this, for instance. Each new window on the early universe has the potential to reveal surprises that force us to rethink our theories. Of course, there's also the possibility that future observations will simply confirm the standard picture of inflation leading to the hot Big Bang, with no clear signatures of what came before. In that case, we might be stuck with the underdetermination problem. Multiple theories would remain viable, and we wouldn't be able to choose between them based on observations alone. But even that would be progress in a sense. We would know the limits of what we can know, which is itself a kind of knowledge. There's something profound and humbling about reaching the boundaries of scientific investigation. For most of human history, the origin of the universe was the domain of religion and mythology. Different cultures told different stories about how the world came to be. Stories involving gods and cosmic battles and primordial chaos. Science, particularly over the last century, has transformed this into a domain where we can make precise mathematical models and test them against observations. We've pushed back the veil of ignorance to within fractions of a second after the Big Bang. We have equations that describe the evolution of the universe from that point forward, and those equations match observations with remarkable accuracy. This is an extraordinary achievement. But we've now reached a point where we are confronting questions that might be at or beyond the limits of what science can answer. Not because we lack intelligence or technology, though we certainly lack a complete theory of quantum gravity, but because the questions themselves might not have empirical answers. What came before the Big Bang? Maybe nothing. Maybe another universe. Maybe a timeless quantum state. Maybe the question is meaningless. We've seen that each of these answers has sophisticated mathematical frameworks behind it, and some of them make predictions that we might be able to test. But there's a real possibility that we'll never know for certain. And you know what? That's okay. One of the most important lessons from the history of science is that our ignorance is not shameful. It's the starting point for investigation. Every question we've answered has revealed new questions we didn't even know to ask. When Newton explained gravity, it seemed like a complete theory. Then Einstein showed that Newton's gravity was an approximation that breaks down in strong gravitational fields or at high speeds. When we developed quantum mechanics, it seemed complete. Then we discovered problems applying it to gravity and cosmology. This process of discovering the limits of our knowledge and pushing beyond them is what science is about. The fact that we're now seriously discussing what happened before time began is a testament to how far we've come. A few centuries ago, the question would have been dismissed as theological speculation. A few decades ago, it would have been dismissed as untestable metaphysics. Now, we have multiple mathematical models, some of which make predictions we can test. That's progress, even if we haven't reached a final answer, and there's something beautiful about the fact that the universe is more mysterious than we imagined. If we could explain everything, if there were no deep questions left to puzzle over, the cosmos would be a less interesting place. The persistence of mystery gives us something to strive for, something to wonder about. It reminds us that we don't have all the answers and maybe never will. That's not a reason to stop asking questions. If anything, it's a reason to keep asking them. There's also value in the journey itself, independent of whether we reach a destination. The process of thinking carefully about what came before the Big Bang has led to profound insights about the nature of time, space, quantum mechanics, and gravity. It's driven the development of new mathematical techniques and new ways of thinking about physics. It's forced us to examine our assumptions and to think more clearly about what we mean by fundamental concepts like existence, causation, and explanation. Even if we never definitively answer the question of what came before the Big Bang, we'll have learned an enormous amount in the attempt. And who knows, maybe the question itself will transform. Maybe future physicists will look back at our current formulation of the question and realize we were asking the wrong thing, that we were confused about the concepts involved, that the real question is something we haven't even thought of yet. This has happened before in the history of science. People used to ask what substance fills space, what the aether is made of. It took Einstein's special relativity to show that the question was based on a false assumption. There is no ether. Space doesn't need to be filled with substance for light to propagate. The question dissolved rather than being answered. Maybe that will happen with the question of what came before the Big Bang. Maybe we'll realize that we're smuggling in assumptions about time and causation that don't apply in the quantum gravitational regime. Maybe the question will be replaced by a better question that we can actually answer. Or maybe not. Maybe the question will persist, tantalizing and unanswerable, a permanent reminder of the limits of human knowledge. There's something poetic about that, too. We are, after all, small beings on a small planet orbiting an ordinary star in an ordinary galaxy, trying to understand the origin of everything. The fact that we can even formulate the question, that we can write down equations and make predictions and design experiments to test them, is itself remarkable. Whether we ultimately succeed in answering the question is almost beside the point. The attempt is worthwhile in itself. Let me try to put this in perspective by zooming out. Right now, as you listen to this, you're sitting on a planet that's 4.5 billion years old. That planet formed from the debris of previous generations of stars that lived and died, creating the heavy elements that make up your body. Those stars formed from hydrogen and helium that were created in the first few minutes after the Big Bang. The Big Bang happened 13.8 billion years ago, setting in motion a chain of events that eventually led to your existence. And the question we've been exploring is what, if anything, existed before that moment? The fact that you can even contemplate this question is a result of billions of years of cosmic evolution. The atoms in your brain were forged in stellar furnaces. The neurons firing as you think about this were shaped by millions of years of biological evolution. The concepts you're using to understand the question were developed over centuries of human intellectual progress. You are, in a very real sense, a way for the universe to think about its own origins. That's not mysticism. That's just an acknowledgement of the fact that we're made of the same stuff as everything else, organized in such a way that we're capable of self-reflection and inquiry. When you ask what came before the Big Bang, the universe is asking that question about itself through you. Consciousness and intelligence are not separate from the physical cosmos. They're part of it, emergent properties of matter and energy organized in particular ways. So, the question of cosmic origins is not just an abstract intellectual puzzle, it's deeply personal. Understanding where the universe came from is, in a sense, understanding where we came from. Not just our immediate origins as biological organisms or as a species, but our ultimate origins as complex patterns of matter and energy. And maybe that's why the question is so compelling. It's not just curiosity for curiosity's sake. It's a search for meaning, for context, for our place in the grand scheme of things. Different people will draw different conclusions from the scientific theories we've discussed. Some will find comfort in the idea that the universe might be eternal, with no ultimate beginning or end. Others will be disturbed by the same idea, finding it cold or purposeless. Some will be awed by the notion that the universe could have tunneled into existence from nothing, a quantum fluctuation writ large. Others will see this as inadequate, as merely pushing the question back rather than answering it. Some will embrace the multiverse, finding meaning in the idea that all possibilities are realized somewhere. Others will reject it as unfalsifiable speculation. These different reactions are understandable because we're not just thinking about physics here. We're thinking about existence itself, about meaning and purpose and the human condition. Science can inform these reflections, but it can't dictate how you should feel about them. What science can do is provide a framework for thinking clearly about these questions, for distinguishing between what we know, what we can know, and what might be forever beyond our reach. It can show us that the universe is stranger and more wonderful than we imagined. It can reveal possibilities we never dreamed of. It can challenge our assumptions and expand our horizons. And it can remind us that mystery is not a failure of knowledge, but an invitation to wonder. As I bring this exploration to a close, I want to acknowledge that we haven't arrived at a definitive answer to the question of what came before the Big Bang. How could we? It's one of the deepest questions humans have ever asked, and we're still in the early stages of being able to address it scientifically. What we have done is survey the landscape of possibilities. We've seen that quantum mechanics might allow a universe to tunnel into existence from a quantum vacuum. We've seen that time itself might not be fundamental but emergent. We've seen that the Big Bang might not be the beginning, but a transition from a previous state, whether that's a contracting universe that bounced, a previous aeon in an infinite cycle, or a collision between higher dimensional brains. We've seen that the universe might be part of an eternally inflating multiverse with no beginning or end. And we've seen that some of these ideas might be testable, at least in principle, through observations of the cosmic microwave background, gravitational waves, and other phenomena. The coming decades will be exciting as new observations either confirm or rule out various models. But we should prepare ourselves for the possibility that the question might not have a scientific answer, that what came before the Big Bang, if anything, might be forever hidden from us by the veil of the Planck epoch. That wouldn't make the question meaningless. It would just mean we've reached the boundary of what science can tell us, and we have to be satisfied with that. In the meantime, we can marvel at how far we've come. A century ago, we didn't even know the universe was expanding. We thought the Milky Way was the entire cosmos. Now, we're discussing what happened before the Big Bang using sophisticated mathematics and testing our ideas against precision observations. That's extraordinary progress by any measure. And the journey continues. The next breakthrough in quantum gravity, the next surprising observation from cosmology, the next insight from a theoretical physicist working late at night on equations we can barely understand. Any of these could transform our understanding. We live in a golden age of cosmology, where the deepest questions about existence are being seriously addressed by science. Whatever comes next, whether it's a definitive answer to what came before the Big Bang or a deeper appreciation of the mystery, will be worth the wait. So here we are, 13.8 billion years after the Big Bang, or perhaps infinitely many years into an eternal cosmic story, asking how we got here. The universe began, if it began at all, in a state we can barely comprehend. It expanded, it cooled, it formed stars and galaxies and planets and eventually us. And now we're trying to understand it all using the laws of physics that we've painstakingly discovered, pushing those laws to their absolute limits and perhaps beyond. We don't know what came before the Big Bang. We might never know. But the fact that we can ask the question, that we can think carefully about it, that we can propose theories and test them and argue about them, that's something remarkable. That's the human mind at its best, grappling with the deepest mysteries of existence. And in the end, maybe that's what matters most. Not the answer, but the question. Not the destination, but the journey. Not certainty, but wonder.